Pilot wave theory, also known as Bohmian mechanics, rests on a set of fundamental principles that distinguish it from other interpretations of quantum mechanics. It proposes a deterministic universe, one where the behavior of particles, while appearing random at the macroscopic level, is governed by precise underlying laws. One of the key tenets of pilot wave theory is the concept of realism. Unlike the Copenhagen interpretation, which suggests that particles do not have definite properties until they are measured, pilot wave theory posits that particles possess these properties at all times, regardless of whether they are being observed. This implies the existence of hidden variables, additional pieces of information not captured by the traditional quantum mechanical description, which determine the particle's behavior. Another crucial aspect of pilot wave theory is the idea of non-locality. This principle suggests that events happening in one location can instantaneously influence events in distant locations, even if these locations are separated by vast distances. This seemingly spooky action at a distance arises from the interconnectedness of the guiding wave, which can instantly transmit information across the universe. This theory, also known as Bohmian mechanics, was first proposed by Louis de Broglie in 1927 and later expanded by David Bohm in the 1950s. One enigma was the wave-particle duality, a fundamental concept in quantum mechanics that describes how particles like electrons can exhibit both wave-like and particle-like behavior depending on the experimental setup. The perplexing observation that particles like electrons could exhibit both wave-like and particle-like behavior had long puzzled scientists and led to numerous debates and interpretations. Pilot wave theory addressed this by proposing that particles are always guided by a wave, known as the pilot wave, which determines their trajectories. Even when particles appear to behave like discrete entities, they are still influenced by this underlying wave, which provides a coherent explanation for their seemingly dual nature. The wave, in essence, dictates the particle's motion, guiding it along specific trajectories that give rise to the observed wave-like patterns in experiments such as the double-slit experiment. These specific trajectories result in the interference patterns observed in the double-slit experiment, a hallmark of wave-like behavior in quantum mechanics. Another puzzle that pilot wave theory shed light on was the mysterious process of wave function collapse, a concept that has been a cornerstone of quantum mechanics since its inception. In traditional quantum mechanics, the wave function, a mathematical entity describing the state of a quantum system, was thought to collapse upon measurement, instantaneously forcing the system into a definite state. Pilot wave theory, however, provided a more natural explanation. It suggested that the wave function never actually collapses, but rather evolves smoothly and continuously over time in accordance with deterministic laws. The apparent collapse, according to this view, is simply a consequence of our limited knowledge about the particle's initial conditions. As we gain more information, the wave function appears to collapse, but in reality, it is just our understanding that is becoming more precise. As the particle interacts with its environment, our uncertainty about its position decreases, giving the illusion of a sudden collapse. This perspective aligns more closely with classical physics and provides a bridge between the quantum and classical worlds. Perhaps the most striking example of pilot wave theory's explanatory power lies in its resolution of the famous Schrödinger's cat thought experiment. This thought experiment, designed to highlight the absurdity of applying quantum superposition to macroscopic objects, imagined a cat trapped inside a box with a device that could release a lethal poison, the trigger for this device linked to the decay of a radioactive atom. The trigger for this device was linked to the decay of a radioactive atom, a process governed by the principles of quantum mechanics and subject to the probabilistic nature of quantum events. According to the Copenhagen interpretation, the cat would exist in a superposition of states, both dead and alive, until the box was opened and an observation was made. This scenario, while mathematically consistent, seemed to defy common sense and raised questions about the nature of reality. Pilot wave theory, however, cut through this paradoxical scenario. It proposed that the cat was never in a superposition to begin with, thus avoiding the need for such a counterintuitive state. Instead, the cat's fate was predetermined by the hidden variables associated with the radioactive atom and the measuring apparatus. These hidden variables, which are not accounted for in the Copenhagen interpretation, provide a deterministic framework for understanding quantum events. To fully appreciate the significance of pilot wave theory, it's essential to understand the context in which it was developed. This brings us to the Copenhagen interpretation, a collection of views about the meaning of quantum mechanics that originated from the pioneering work of Niels Bohr, Werner Heisenberg, Max Born, and others. While the term Copenhagen refers to the Danish city where much of this foundational work took place, the use of interpretation was apparently coined by Heisenberg in the 1950s to refer to ideas developed during the 1925–1927 period. It's worth noting that there is no definitive historical statement of what the Copenhagen interpretation entails, as it glosses over some disagreements between its key proponents. Common features of the Copenhagen interpretation include the belief that quantum mechanics is intrinsically indeterministic, with probabilities calculated using the Born rule. This interpretation also introduces the principle of complementarity, which states that objects have certain pairs of complementary properties that cannot all be observed or measured simultaneously. For instance, you can't precisely measure both the position and momentum of a particle at the same time. Another cornerstone of the Copenhagen interpretation is the idea that the act of observing or measuring an object is irreversible, and that no truth can be attributed to an object except according to the results of its measurement. In other words, it rejects counterfactual definiteness, the notion that we can meaningfully speak of the properties of a quantum system independent of measurement. Copenhagen-type interpretations hold that quantum descriptions are objective, meaning they are independent of physicists' personal beliefs and other arbitrary mental factors. Despite its widespread acceptance, the Copenhagen interpretation has faced numerous objections over the years. Critics have pointed out the discontinuous and stochastic nature of the observation or measurement process, the difficulty in defining what constitutes a measuring device, and the seeming reliance on classical physics to describe such devices. Several experiments have provided support for pilot wave theory. One such experiment is the oil droplet experiment, where droplets of oil bounce on a vibrating fluid surface, creating wave patterns that guide their motion. This macroscopic system exhibits behavior strikingly similar to the pilot waves proposed in quantum mechanics, offering a tangible analogy for the theory. However, pilot wave theory is not without its criticisms. Many in the scientific community argue that it complicates the elegant simplicity of the Copenhagen interpretation without providing additional predictive power. They contend that the introduction of hidden variables, while conceptually appealing, has yet to yield new, testable predictions that could distinguish it from the standard quantum mechanics framework. Despite these criticisms, pilot wave theory continues to intrigue physicists and philosophers alike. In conclusion, pilot wave theory provides a fascinating lens through which to view the quantum world.